know this isn't acid bases, but let's talk about that part as well. Does it dissolve? Sodium chloride, does it dissolve in water? That wasn't supposed to be a hard one. Yes, sodium chloride dissolves in water, right? That's salt. We've added that to water. We see that it dissolves. Yes. Okay, so we could say, I know it because I've seen it. How else could you say that sodium chloride dissolves in water? How do you know it's aqueous? How do you know the phase? Theoretically, it was something you did when you talked about chemical reactions, particularly double replacement reactions or double displacement reactions in Chem 151. You looked at things known as the solubility rules. And rule 1 of our solubility rules is anything with a group 1 metal is always soluble in water. So if I have sodium bonded to anything, sodium's a group 1 metal, it should dissolve in water. Okay? If I now ask silver chloride, does silver chloride dissolve in water? Okay? Yeah. Perfectly acceptable face because you're like, I don't know any of the solubility rules. That's perfectly fine. That's okay. Okay, but the point that I'm trying to get you to think about is you learned about those solubility rules and we talked about them as absolutes. They either all dissolved or they didn't dissolve, and that was it. But we just spent 4 weeks talking about there are no absolutes. They go both directions, which means what we can go through and do with our solubilities is we can now evaluate how much does dissolve, because some does dissolve. Why would that be useful to us? Right? We can go back to our acid-base chemistry. What are we looking at in this area or this picture?
Bleached coral.
Bleached coral. Okay, cool. It's coral. Why is it bleached? The ocean was acidic. Okay? Killed off the coral. It could no longer produce the materials it needs to absorb sunlight, which means we lose all the colors behind it and we get bleached coral. Okay? If we push on it further, we could go through and look at what combines or what comes together to make coral. You're looking at usually some kind of skeletal structure, which is usually a combination of calcium, and you're looking at calcium carbonates. What's special about calcium carbonates? They're very insoluble in water, which is why we can see corals when they're made out of it, because they don't dissolve. Right? Makes perfect sense. Except if the water is acidic, what starts to happen? It starts to dissolve. Right? That dissolving process starts to destroy the skeleton of the structure or of our corals, and that then causes problems. If it can't maintain its skeletal structure, it falls apart. Okay? And it can no longer live. So when we're talking about this unit, we're going to bring in both the concepts of acids and bases and the concepts of solubility, because they're both going to be tied back to our equilibrium expressions and how we manipulate and use the stuff that we just talked about within equilibrium to these very specific situations. Okay, so one of the questions that can come up right away is, how does CO2 emissions cause ocean acidification? Does anybody know? Where is CO2? What phase? That's a gas, so that's up in the air. Where's the ocean? Not in the air. So why is something in the air causing something not in the air to have a problem?
Rain.
Okay, so rain is water, right? Why does that matter? Say again? Okay, but why does that cause ocean acidification? Gets CO2ified. That's kind of cool. So what we're talking about now is a chemical reaction between CO2 and water. When those two chemically react, guess what they produce? Acid, which is why the oceans get acidified. Right? Because you've got CO2 in the air, that's going to be across the surface of the water, and that can now react with the water on that surface and turn into an acid. That acid can now be dissolved into the environment, become aqueous, and can now travel through all parts of our potential ocean. Okay? That's something that we need to be concerned about if we care, arguably, about the existence of our planet. So, what are some examples of everyday substances that are acids or bases that you know of? We're in our blue box situation, so blue box means? Yeah, talk. Words from your mouth, share at your table, come up with some ideas. Baking soda was baking soda. Okay, baking soda is actually an interesting one. I want to place it as oh geez, I swapped all the letters. I have to look at the formula. I'm not positive about the sodium bicarb. As sodium bicarb, it can technically act as both an acid or a base. Other ideas? When we're using baking soda, we're almost invariably using it as a base. Okay. Baking soda is a fun one because when we're talking about sodium bicarb, what we're looking at is the system to produce CO2. Why would we want to produce CO2 when we're baking? To make bread rise. Okay, so you mix in a little bit of an acid, the acid reacts with the base, it produces CO2, the CO2 bubbles form and add fluff, for lack of a better descriptor, to what our item you're baking with. Where else might we want to get rid of CO2 or produce CO2? Say again? Soda? Okay, if you go through and look, the compound that's actually initially produced when we take baking soda and react it with an acid is carbonic acid. Where is carbonic acid found? Sodas. Okay, so that when you release that seal, that's the carbonic acid trying to go back up to that carbon dioxide, and that's what's getting you that bubbling. Where else do we want to worry about CO2? Yeah, our respiration process. How do we navigate and get CO2 from our muscles, where it's produced, to our lungs so that we can exhale it? Right? That's passing through effectively a bicarbonate buffer system in your blood. And by changing the pH, which we'll get to, the acid content within our blood, we can change the solubility of the carbon dioxide and cause it to be released in the lungs, okay, or absorbed in our muscles so that it can be transported towards our lungs. All right? So acids and bases show up in lots of different places, so we need to get some context of what makes them acids and bases. Looking at the names is pretty useless. What we should do is start to shift towards both the structures of what makes them acids, and potentially, if we looked at enough structures, we could then start to define what they had in common. All right, so we'll jump to the crux of it. What they have in common, okay, is that acids lose NH+, okay, when it reacts with water. Okay, the when it reacts with water becomes kind of a weird statement, okay, at least from an organic chemist point of view. Why would an organic chemist care about that? What is organic chemistry about? Carbon and hydrogen compounds. And carbon and hydrogen compounds are nonpolar covalent bonds which generate London dispersion forces. And if we look at water, water is a polar covalent bond that generates hydrogen bonding forces. Would we expect those two systems to mix? No. Theoretically, that was something you talked about in 151 because we didn't talk about it in 152. Okay? You did a lab kind of based on that with colligative properties at the beginning of this semester. So you could use intermolecular forces. So an organic chemist typically doesn't want to see water in their chemical reactions because water does all sorts of nasty other secondary reactions that we don't want to deal with. Okay? But if we get rid of the water, does that change our definition? Well, if the definition says when it reacts with water, yes, that's going to change our definition a lot. And so when we talk about the history of acids and technically bases and their definitions through history, they are constantly refined and adopted. What's being displayed here is a somewhat modified version of the Arrhenius definition of acids and technically bases on the next slide. Okay? That Arrhenius definition was very centralized on how it responds and reacts with water. Why did Arrhenius 500 years ago care about reactions with water? Why should you care about reactions with water? Several of you have bottles on the table. What's in your bottle? Water. Some of you have things that aren't water. You've got coffee. Really? How does your coffee cold? Ice. What's ice? Water. Okay? Water. It's in our blood. It's in our breath. It's everywhere around us. I don't remember the number, and I always quote it wrong, but was it 70 to 80% of the earth is made up of water? Okay? Water is such a prevalent liquid phase, and ultimately solids and gases, that it is kind of our central solvent for all of our chemical reactions. It's such an important solvent that we actually invented a phase. What are the phases of matter?
Solid, liquid, gas.
Cool, solid, liquid, and gas. None of those mention water. What's the phase we invented? Aqueous. We add the aqueous phase. That's a mixture, not a pure substance, which is why it's not a standard state of matter. Okay? But it is such an important phase to go through and specify because all of our reactions run in water. Okay? We're the vast majority of them. Okay? That's why Arrhenius was so focused with water, because he's taking these substances and placed them into water and then saw a potential chemical reaction come out of it. It is that observation that coins now the definition. Okay? Within that definition, it's losing an H plus when it reacts with water. I'll give you a little bit of context for the future if you needed organic chemistry. We typically talk about acids as H plus donors. Flip that around. An H plus donor. Okay? Same concept, is just looking at it from a different perspective. Okay? So if we look at the general form of our acid is that we take, should have gone through that sign, is that we want to mix water with whatever our acid is. Why do we write HA? Why did we write H? H is hydrogen, yes. Why did I need the hydrogen? Because we're talking about an acid. And acids, by definition, need to lose a hydrogen, which means our acid must start with at least one hydrogen. So we have to see the H. What's the A represent? It represents the rest of the structure. Why do we pick the letter A? Because we're trying to say it's an acid. That's it. Okay? So if we're now going to run this chemical reaction, HA is going to lose that H plus. Okay? In a chemical reaction, it has to lose it, but something else would have to pick it up. That something else is our water. So if we're now going to predict what the products should be in this scenario, what needs to happen to the HA? Well, number one, what do I have to get rid of? H, which means my symbol becomes, keep it simple, A. That's it. We'll worry about the other part in a second. Okay? H2O has to be the thing that's picking up that hydrogen, which means its notation is going to have to become H2O, right? Because we've added an extra H to it. That looks a little bit silly, and we would typically argue that that's a wrong way to write it, and so we would write it instead as H3O. All we're talking about is putting that atom, taking the atom off one place and putting it on another place. That's it. So far, so good? But it's more complex than that, right? Because is that all that changed? What else changed? The charge. Where's the charge specified? In the acid? Where do you see the charge in HA? Okay? And I want to lean on that a little bit because we heard it's on the acid. Great. And then I said circled HA, and all of a sudden we got a response for the sake of the recording of, I don't know where the charge is. That's not what I was talking about. Right? Well, it's what I'm talking about. Where's the charge on HA? 0. It's there. It's 0. Where is that 0 specified? The upper right-hand corner. Every time you look at a chemical formula, the charge is given to you. It's given to you in the upper right-hand corner every single time. So if I look at HA, it has a 0 charge. And if it gets rid of a hydrogen, what charge should it become? We've got to be a little bit careful because I phrased that question in a bit rude of a fashion. If I have HA and I lose a hydrogen, what charge should it become? What charge is a hydrogen? No. A hydrogen ion is positive. Okay? And if we want to get more specific, a hydrogen cation is positive. What charge is a hydrogen? Neutral. So if I start with HA and I lose a hydrogen, what happens to the charge? Nothing. Because when I lose that hydrogen, I'm losing both the positive part of it, the proton, and the negative part of it, the electron. But if we go back to the definition of what makes an acid, are we losing just a hydrogen? No, we're not losing just a hydrogen, because what's the symbol for a hydrogen that has 1 proton and 1 electron? Just H. What am I losing? H plus. That charge in the upper right-hand corner gives me a piece of information. That piece of information is that the hydrogen I'm losing is not going with an electron. It stays behind. And if that electron stays behind, what happens to the A?
It's a negative charge.
It is now negatively charged because we're losing that positive aspect, and that's it. So you're trying to look at the balance of your protons and electrons within your individual structures. This is why it's important to understand all the stuff in Gen Chem about our subatomic particles, because they define our positive and negative charges. What happens to the water? Well, it gained that hydrogen, but that hydrogen was positively charged. And if I start neutral and gain a positive charge, what should my charge become? Positive. And that's now what's happening within that overall system. Kind of, sort of? Cool. You do it with HCl. Write out your reaction. So we're going to go through and look at this reaction. We want to understand what's going on with the HCl. I want to react it with water, okay, in a process to predict our chemical reaction. Well, that hydrogen gets donated, okay, or loses the H+. The water accepts it, so I'm going to get H3O plus my Cl is now left over without that hydrogen. Because that hydrogen was positively charged, I want to make sure that I note that that's H3O positive, okay, because it didn't gain an extra electron to make it neutral, and that chlorine would now be negatively charged. I personally like to circle charges so that I don't get them confused with random drawings that I put elsewhere. Kind of make sense? Did everybody write the reaction this way? Everybody's like, yep, I absolutely did. Bullshit. No, you did not. How did you write it? You swapped them around. Does the order matter? No. That becomes a critical statement to realize when we're dealing with our chemical reactions. The order does not matter, and where we're placing those, don't focus on the order, recognize the individual pieces that come out of it. Why? If you naturally run through always matching it to that order and the exam comes in and the exam swaps the order, what's going to happen? Yeah, your brain's going to completely flip off and you're going to have no clue what's going on. And all we did was swap the order. That order does not matter. Okay, why? Because addition is communicative. We can go back to mathematics if we wanted to run that. Okay?
But doesn't swapping the order imply that it's a reversible reaction then?
So 2 things are going to come with that. Number 1, no. Swapping the order of those 2 things in the product, doing it Cl minus versus H3O plus, says nothing about the reversibility of this chemical reaction.
Okay. I thought this was about the reactants and products being flipped. I didn't realize
Nope.
this was about.
Yeah.
Okay, never mind.
Okay? But you do bring up an interesting point. Is the reaction reversible? What did you just spend the last 4 weeks minus last week doing? Saying that Well, frickin' chemical reactions are reversible. So yes, this reaction is absolutely 100% reversible. Okay? And we're going to look at that in a second. So far, so good? Okay. What does a base do? A base is now a molecule that gains H+ when it reacts with water. So if we're going to look at our general format for the reaction, water is going to show up in our general equation just like normal. Nothing's fancy about that. And now instead of using HA or even A, we're going to use B. Why would we use the letter B? Okay, one person laughed, the rest there was nothing. This is supposed to not be a hard challenging question. Base begins with the letter B. We're trying to pick symbols that allow us to navigate the system and how we would move through it. Okay? What happens? The base needs to gain an H+, which means if I look at what happens, that gaining is the chemical reaction. Okay? That's what we're trying to describe in this middle part. That arrow is our gain. Technically our loss also. Okay? But is our gain. We're talking about B gaining an H. What do I have to do? The B needs an H with it. Should it be BH or should it be HB? That's a really hard question for the record. Okay. The order of those two pieces is going to be very arbitrary. Okay, and it's going to be largely dictated based off of the identity of the specifics of what B is. Okay? That's going to dictate whether it should be BH or HB. Because what we're trying to imply by switching that order is something about structure. Do chemical formulas give us structural information? Sometimes, generally not. Okay? Chemical formulas are ultimately pretty useless at providing us that extra context, okay? Which is why when you talk to an organic chemist, the very first thing they try and get you to do is stop drawing formulas because they're awful. The formulas don't provide any context to what's happening within the chemical reaction. Okay? So for your sake, does it matter? No. Okay? In some scenarios, you will be technically wrong, but in my experience, if you ask a chemist why you're wrong, they won't actually know the answer, which is a fun one. Okay? But you can do the same thing with the English language. Which is correct? The black big brown bear? They can't be black and brown. The black big bear or the big black bear? Ooh, why is big black bear correct but not black big bear? I can't even freaking say it. Okay? There's actually a rule that dictates the order you place your adjectives before a noun. Did you know that? Okay? One person in the class, maybe two if you count me, but I'm not sure you should count me. Okay? We're aware of this. It becomes a natural response that we're just used to seeing it written some way. We don't know why it was written that way. We just always follow that. Why is that problematic for students? Do you have the experience to know which way it was written? No, this is why English as second language people get pissed about black big bears. Why is that wrong? You can't tell me that's wrong. Okay? For the same reason, okay, you're going to butt into that situation. Just be aware of it. Not a big thing to stress about. I definitely won't take off points for you on it. Just be aware of it. Okay? Is HB correct, though? So we're cycling all the way back. I know, big shift in gears. If I write HB, am I correct? No, why not? Okay. The hydrogen that I gained was positively charged, right? All of those rules of positives and negatives that we talked about with the acids also come back to our bases. If the base was neutral and it gained a positive hydrogen, I need to write it as HB positive. I have to ensure that that charge is located there. Where did the hydrogen come from? It came from the water, which means what's left over? I would have the oxygen and one hydrogen and then a negative charge because I lost the positive. Anybody notice anything interesting about the order here? Which element comes first, hydrogen or oxygen? Oxygen comes first. Why is it not OH2? Did you just notice that? I just saw that. We swapped the order of the things. Why? That's the way it was done. And so now that's the way we do it. Ta-da! And if you write HO minus, I'm pretty sure you'll find some people taking off points. I won't, because I think it's funny. Kind of like Santa. Come on. Nobody? Did you get it, or are you just laughing?
Ho, ho, ho.
Yeah, there we go. Okay. Right? HO. Oh, gee, happy Christmas. Is this on? Let's take a look. Let's take a look at you now trying to do it with ammonia. Not the ho, 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 but try and run the chemical reaction with ammonia. Again, let's drop in our blue box so that we know we're doing that. I want to see how ammonia acts as a base. Give me the chemical reaction. So cool, we could go through and show our products. Nice dragon. I shouldn't have recorded that. One question came up is, why do we not write the charges for our reactants? We did. What's the charge on NH3? 0. It's in the upper right-hand corner. What's the charge on water? 0. It's in the upper right-hand corner. Okay. Why are we suddenly seeing charges in our products? Because what we've done is rearranged charged pieces of those neutral molecules to generate those structures. Okay? Which is a neat question, and I'll draw out some Lewis structures to show that. So did everybody write down what I drew? Okay, again, we should be like, no, we didn't. I didn't write HNH3 plus because that looks stupid, Mike. Why would you do that? Exactly right. There's no reason necessarily for it, but what we're trying to acknowledge is how you shift those across. You decided to group them together, didn't you? And draw NH4 positive. Is the NH4 positive a better way to describe that? Yes, absolutely. All I'm trying to get you to do is to acknowledge that the placement of those atoms may or may not matter depending on those scenarios. Just be aware that you have to shift that hydrogen across. Is that what your question was?
No, I was wondering why is H2 and NH3, they normally have charges, right? So why not?
H2O does not normally have a charge.
NH3?
Does not normally have a charge. Okay. Figuring out those charges is going to go back to ultimately Gen Chem, our 151 classes. When you talked about Lewis structures, how you figure out your balance of your charges and all of that, that's looking at the Lewis structures. What's your end goal? What are you aiming for? No. You personally, your academic career. Mechanical engineering, you don't care. Right. If you're one of those people that's trying to do anything in pre-med or chemical engineering, you're going to care because you have to pass through organic chemistry. In organic chemistry, we're now going to get very specific about how we put together those structures. Okay? Arguably, putting together structures is very important for mechanical engineering, just not molecular structures. Okay? So if we go through and look at the Lewis structures for NH3 and H2O, this is what we're looking at. Okay? What's happening chemically in this process? Well, we said we took H, okay, I'm going to pick the one closest to it. We took that hydrogen. Okay? How many electrons does that red hydrogen have associated with it?
The hydrogen subbonds.
Is the hydrogen connected to the bond? Yeah, that's why the line is there. So yes, that does become relevant. Okay? So that is important, acknowledging the presence of the bond, which means that hydrogen has access to 2 electrons. Okay? Because a line is 2 electrons. When it gets rid of that H+, I drew the wrong one. Damn it. We'll come back to that one in a second. When we go through and talk about the base gaining an H+, where did it get the H+ from? It got it from the water. We're going to run the same argument with the hydrogen connected to the water. is that hydrogen, or does it have electrons? It has access to those 2 electrons. But when it gets transferred, is it taking those 2 electrons with it? Is it taking any of the electrons with it? No, it's not. That hydrogen atom is now just going to be associated with the nitrogen. Well, what part of the nitrogen is it going to be associated with? If we go through and look at what you guys wrote, you had NH4 plus, right? Where are the hydrogens? What are they connected to? There's 2 electrons shared with each of them, connected to what? What's on the other end of the bond with a hydrogen? The nitrogen. How did the hydrogen get associated with the nitrogen? How did it make that bond? There's a pair of electrons there. That pair of electrons shares with the hydrogen. The bond goes to the oxygen. The net result is that we see a bond between our nitrogen and our hydrogen. What happened to the oxygen? It now has an extra pair of electrons. Did you guys talk about formal charges in Gen Chem? Yeah? How do you calculate formal charge? I don't know what that means. It's fine. You don't have to know what that means either. Okay? Every general chemistry class is different theoretically in that. Okay? Hopefully, sort of. You would have learned about formal charge, and the way we calculate formal charge is you look at the valence electrons your atom had, and then you subtract the electrons that are associated with it currently in its new drawing. So when we go through and look at that oxygen, it starts with 6 valence electrons minus 6 non-bonding electrons minus 1 bond. What charge do you get? -1. What was the charge on the oxygen? A -1. Why? That's the why. What did we show? We just said it was -1. What happened to the nitrogen? Well, nitrogen became positive. How did it become positive? How many valence electrons does nitrogen have? 5 minus the number of non-bonding electrons. Non-bonding electrons. How do you know you have a non-bonding pair of electrons or non-bonding electrons at all? You have dots. Do we have any dots? No, which means 0 minus 4 bonds. What do you get? 1. Okay, and because we care more about the sign on it than the number, it's not just 1, it's +1. There's the positive charge that came out of our other formula. And that's all based off of those connectivities. I doubt it. I genuinely don't know because I don't have the quiz, but I doubt it. What you need to be able to do is to process what we walked through initially to get the charges. Okay? And that goes through based off of knowing it's H+. You're told the definition as opposed to why it actually works. Kind of make sense? Okay. So, one of the things or alternate definitions that you'll typically hear with acids and bases is instead of talking about gaining and losing H+, you can talk about the acceptor and donor definitions. Okay? And you'll typically hear people reference it not as H+, but as a proton, right? Which is a very dangerous kind of phrase to kind of toss around, because what do we know about protons? There it is. Protons are subatomic particles found in the nucleus. And if we're going to talk about gaining and losing protons, that sounds an awful lot like changing the identity of the element, right? Or if we want to push really hard on it, we could call that nuclear chemistry. We aren't doing nuclear chemistry when we're talking about acids and bases. We're talking about gaining and losing a proton is talking about what is being transferred. It's H+. Well, what is H? H is a hydrogen. What is H? Or sorry, I was going to say the same thing again. What is hydrogen? One proton and one electron. Except when we talk about acid and base chemistry, does it have the electron? No. So what's left over? One proton. So we can talk about our acid and base chemistry as the transfer of a proton, because that's all that's actually moving around. The thing that becomes a little bit dangerous is that when we're talking about that transfer of that proton, we're not talking about it nuclear. I'm not talking about the proton of our hydrogen being absorbed by our base. Okay? It's not going into the nucleus. All we're saying is that that one proton is now chilling on the outside of our base structure. Kind of, sort of. So we have to be careful to keep those two things separate from each other. Not nuclear chemistry. We're just talking about the sheer definition of that piece. Kind of makes sense? Right. I want to add one more thing to this because it's popping up in OChem. What does this 1 mean? That one right there. What gets written in the upper left-hand corner? Mouth something back there? No? Cool. The mass. What contributes to mass? Protons and neutrons. Because we're looking at hydrogen 1, okay? We know hydrogen has one proton because if it had any other proton, it wouldn't be a hydrogen. Okay? And so if I see that 1 written in the upper left-hand corner, I now know that it has 0 neutrons, which is one of the reasons why I can call it a proton. Okay? What would get written in the lower left-hand corner? What gets written down here? Say again? Yeah, just the number of protons. Okay? So we could look at this and be like, if I wanted to figure out the number of neutrons, I could take my mass number, subtract my atomic number, I get 0, and I get 0 neutrons. What element is this? What symbol is helium? Is that right, HE? Careful. Is it 2 protons? No, it's the mass number is 2. Okay? And if it was helium, would that make sense? Why would that not make sense? That's what the atomic periodic table says. I don't care what the periodic table says. Why can I not have an element with just 2 protons? There's no neutrons. Cool. Why does that matter? Yes, that's lovely. Yes. When I bring 2 protons near each other, what do? They repel away, which is why every time you add a proton, you must also, not an electron, add a neutron to keep them together in the nucleus. This was the belt of stability. Remember, we talked about that real briefly, and we never talked about it again, I think. Okay, but we did at least talk about it. Okay, that's why we had to add those things. So if I'm seeing this 2 with D, it can't possibly be 2 protons. So what is it? A proton and a neutron, which would be helpful if I added the number of protons underneath it. And what element am I talking about? What element has only 1 proton? Hydrogen. Why am I using the symbol D? Because this was something we studied, a special form of hydrogen. That special form of hydrogen is known as deuterium. Okay? Deuterium is an isotope of hydrogen. We decided to give it a new symbol. Why? Because we use it a whole bunch. Okay? This becomes a common knowledge thing that you're supposed to have learned before you achieve organic chemistry. Okay? More than likely you won't, and you'd have to get reminded anyway in OChem. Okay? But just wanted to take that moment to address what's going on with that. Okay? We can then look at conjugate acid-base pairs. Okay? So we've got formic acid here, HCOOH, and a Lewis structure. Okay? What I want you to go through and do is draw the chemical reaction. Blue box. You likely wrote down one of these two possible formulas. Which one is correct? Second one's correct. Why? Which hydrogen is removed? Because what we're talking about is the connectivity of where that hydrogen is. But what did we just say about chemical formulas? They don't give us any information about connectivity, which means ultimately, if this is what you wrote down, you are wrong. What you should instead be writing down would be looking at the Lewis structures. And if you wanted to run the chemical reaction with our water, you would end up with one of two possible options. Or this one. Which one is correct? And that usually stumps students, right? Because you're getting lost in the structures and getting too confused about it. The only thing you need to be concerned about is the difference between those two structures. What is the difference between those two structures?
Which H was removed?
If I look at these two structures, do you see an H? The only place you see the H that was removed is in the starting material. And if I look at these starting materials, they look identical because the H is still there. What's the difference?
Where the electrons are?
There it is. So it's not focusing on the H, it's instead focusing on what's remaining after the H has been lost. What's remaining? Where the negative charge is located. So now it's focusing on that. Would I expect carbon or oxygen to be better at maintaining that negative charge? How would I know that? Okay, again, back to 151, we learned lots of trends, okay, on the periodic table, and one of those trends we learned about, and since you said the correct answer, I'm going to push you, is what trend? Yeah, there it is. We can go to electronegativity trends. Oxygen is more electronegative than carbon, which means what is it doing with the electrons? It's holding them better than carbon would. Which means if I'm going to talk about which hydrogen to remove, I care about the bottom one because it's going to produce the more stable base, and we'll come back to that labeling in a second.
How do you know the first one, the carbon, has the electron?
Where did the hydrogen come from? So in that first one, I'm taking the hydrogen away from the carbon. That's why the charge is going to the carbon. And the second one, I'm taking the hydrogen that was connected to the oxygen. Does that make sense?
Yep.
So because oxygen has a stronger bond with hydrogen.
Ooh, does it have a stronger bond? Because it's more electronegative, it's actually a weaker bond.
With the hydrogen?
Mm-hmm. Okay. So cool, that would allow us to predict that. Do you need to be concerned about that? How many times have you seen Lewis structures in this semester? For everybody saying 0, that's rude. You're literally staring at one on the screen. You've seen it once, okay? Is it reasonable for you to expect to be able to pick that kind of characteristic out? Probably not. I would not be surprised if Alex is going to have you rank relative acid-base strengths, okay, based off of certain rules. The rules that are associated with those are what we just touched on. Okay? Your textbook will list out a sequence of rules if Alex asks, okay, and it usually starts with the size of the atom that had the hydrogen. The larger the atom, the more likely that hydrogen is acidic. When we look at carbon versus oxygen, they're in the same row. There's very little difference in size. Okay? After that, it moves to electronegativity. After that, it moves to the amount of oxygens around it. Okay? And there's a bunch of kind of weird rules that are ultimately coming from the structural analysis that we've decided to not teach you in Gen Chem. I think that's a cardinal sin personally, but who am I to decide? Okay? So when we're going through and doing this, we need to address the next part. Okay? As I believe Dylan noted earlier, we said that we were in equilibrium reactions, right? Which means when I go through and do an equilibrium, you're totally not going to do that the way I wanted you to do it. You freaking butts. I have to acknowledge that this reaction is what? Reversible. So if I look at the reverse reaction, what is this species acting as? To go from here to here, what did it do? It gained a hydrogen. If it's gaining an H+, what did it act as? Awesome. Base. What happened to our H3O+? It lost a hydrogen, therefore it is an acid, right? Everybody good? Plot twist, that was talking about the reverse reaction. What happened with the forward reaction? What did we say formic acid reacted as? An acid, which means the water acted as? Cool. Which species is the acid? Which species is the acid? We've got a dilemma here. There's two species that are acids. Depending on which side of the reaction we're looking at or talking about, it becomes very confusing to label one as an acid. Because I have an acid in the forward direction and I have a different species that is the acid in the reverse reaction. So I need to add some language to clarify that. What language do I want to add? Big bold letters at the top of the screen. Conjugate. Okay. So as a kind of blanket statement, acids and bases are typically reserved as labels for the left-hand side of the reaction, or quote-unquote reactants. What's on the right-hand side of the reaction? Are conjugate acids and bases. And if we now want to get through and get real fancy, we can reference those two species with the green arrow as conjugate acid-base pairs. We can reference the other two as conjugate acid-base pairs. Okay? That's the point of adding that extra term, to give us an extra layer of information so that we can be a little bit clearer about that system and we know how those species are tied. Okay? Note, we don't have an orange arrow where I would take this acid and rank it to that acid. Why not? Their structures have nothing to do with each other. That's why not. Okay? Very clearly, I paid no attention to time.